All right, welcome back to pycse. Today we're going to take a look at solving an ODE with event functions that allow us to capture properties of our solution. So we'll look at this differential equation down here. The solution, you'll see in a minute, looks kind of like this. It oscillates and crosses zero a couple of times. It has minimas, it has maximas. And what I want to do is look at how we can leverage solve IVP to capture those points and maybe do something with them. All right, so let's start by just solving the IVP so that we can see what it looks like. So we have to import a few things. We have to define our ODE. So we use a function that has the signature xy or ty if you prefer. And we just need to return the right-hand side of that. All right, so there is the ODE that's solved over here. Now we just have to call solve IVP. And we pass in the ODE. Let's do, the time span has to start at the initial condition, so it starts at -1. And we'll go to 20. And then we have to give it the initial condition, -0.5. And this has to be a 1D thing. It's a good idea to make it an array, but many times you can get by with just a tuple or even a list. And then let's plot this real quick. So the solution here comes out as a structure, and the x values are in sol.t, and the y values are a 2D array in sol.y. And so I often just transpose this so that it's a column, and then we'll get a plot. All right, so this isn't super nice. There's it's kind of discrete, so let's make it a little bit smoother by adding a max step equals 0.1. And maybe this is supposed to be 0.05. That looks better. That's probably a mistake, yeah, in here. All right, so it's 0.05. So you can see here we have the minimas. Across here we have several maximas, and then across here, why don't we add a horizontal line at 0, and you can see where those are. Maybe we'll make it a black line. Okay, black line. So our first goal is going to be finding the zeros. Those are the easiest things to do, and the standard way of doing this is to create an event function. So the event function has the same signature as the ODE x comma y. And what we need to do is identify the conditions where that event function will be 0. And in this case, it's simple. It's wherever y is equal to 0, and we don't care whether it's how it's 0. Any of them will do. All right, so let's define event 0, x comma y. And we want this one to be when the function is equal to 0, so we're just going to return y. All right, and so that's it. It's very straightforward. And the only thing important to remember is that the way these events are triggered is there has to be a change in the sign of this function. So it has to go from negative to positive or positive to negative in order to be triggered. And then internally, the solver will find the position where it's equal to 0. If it would come down and just touch this and go back up, or go up and just touch it and go back down, then there would be no change, and that is a kind of event that doesn't work very well. So let's do this again. I'll just copy this up here. And what we need to do is add events equals, and I'm going to go ahead and make this an event list because we're going to add a couple of events here. And before we look at the plot, we'll see what comes out of the solution. When we run this now, we're going to see some new information. So the solver successfully reached its conclusion. We have our T array, and Oh, it's kind of large. We also have t events. So now we have an array of events, and this is actually a list, so we'll index it. That tells what times the zeros occurred. And there is also y events, which is for each one what the value of y is. And you can see here they're all basically 0. All right, so let's go back up here and now we'll look at this and plot it. So we'll have this plot, and then let's do plot.plot sol.t events. And we want the events corresponding to event 0. And we want these ones corresponding to 0. And let's see, I think we want those, we'll see if we can make those yellow circles. All right, so I almost, those are not super visible. I don't know if we can choose orange. I don't remember if this is works. All right, that's kind of close enough. You can see that we have found in orange zeros now all of the places that that are zeros. Now, to get the minimas and maximas, we need a different kind of event. And the minimas and maximas are defined where the y derivative is equal to 0. So in the next step, we'll add another event function so that we find these zeros. Let's see. I'll add a label here for 0. And let's go ahead and add plot.legend. And you can see there we have the zeros. All right, let's add one more function now that is, we'll call it event 1, x comma y. And now we want to find where is the derivative equal to 0. And we can do that going back up here to our ODE function. This is the derivative, so we just have to evaluate ODE at these x points and y points. So let's do that. Return ODE x comma y. That is for y prime equals 0. All right, and then we can add here event 1. So now we'll have two events that will be triggered. And we should find here, let's add this and change the index to 1. And let's make this color red. And for now, I'm going to call it y prime equals 0. You'll see why in a minute. Yp equals 0. All right, so this should find all the places where y prime is 0. That's going to be every one of those. And it should put... let's see what happened here. Less than or equal is not supported by tuple and int. Oh. All right, that may be caused by this. Let's say np.array. All right, so usually you can get away with having a tuple or something, but not always, and we just learned that you have to have an array in this case. All right, so this finds us all the places where y prime is equal to 0 and where the function is equal to 0. Now, to get one step further to differentiate the maximas from the minimas, we have to pay attention to a detail in solve IVP. So let's take a look at it. Over here, there is an argument for events, and if you scroll down past all these options to events, then it says it's a callable or list of callables. The function is equal to 0 when you find a crossing, and then we can see there's an option to terminate it, but we don't want that. What we want is this direction. So this determines the direction of a 0 crossing. The default is 0, which means any 0 is good. But you can change the direction to be positive, which means that the event only triggers when your event function goes from negative to positive, or it could be negative, which is the opposite. And that's what we need to use to specify maximas or minimas. So if you're going through a maximum, the derivative is positive and then goes negative. So we set direction to be negative, -1 for example, to find maximas, or +1 to find minimas. All right, so let's go up and modify this this one to be event1.direction equals 1. And this is going to find minimas. And it finds a minimum because as you are approaching a minimum, the first derivative is negative, and then as you go through it, it comes out positive. And so we have +1 here. And then we can just change this to be now minima. All right, so just by adding this direction attribute on here, we should see now when I run this that we have only the red dots on the minimum. Let's see, what is this? I think we can probably ignore this this message here for now. And then we'll add one more function to find the maximas. So event 2 now is still going to be the first derivative, but we're going to make the direction -1. And then down here, we just make this index be 2, and this index be 2, and let's make this color green, and make this a max. All right, and that should list out a range. Oh, we also have to add, let's put it over here, event 2. So now we have 3 events, 0, 1, and 2. The 0th index is the first one, this is the 1 index and the 2 index. And now we see that we have green dots on the maximas, red dots on the minimas, orange dots on the zeros. And that is a good indication that you can apply these events to all kinds of things. You can use it to find, say, maximas in a profit function, or minimas in a cost function, or zeros to find the roots of a function, or anything else you can figure out how to do. All right, let me see what we're doing here that's giving me this error. Probably it is going to be, let's see, the ODE is going to return an array. This is an array. Creating an ND array from ragged nested sequences. Let's see, is it in the, it's not in the plot, right? Nope. So it's definitely happening in here. I have not seen this this before. It is only a warning though, so we don't really have to worry about it too much. But it's an annoying. Oh, is it gone now? No. It's an annoying warning, and I'm not real sure where it comes from. Let's see. So that's all right. That's all right. Those all return floats, so that's interesting. Maybe let's look at this solution. Let's see, we have our solution, there's T. T events is a list of arrays. They have different lengths. That could be the issue. And then the Y events also is a list of arrays, and these have different lengths, which I guess could be the issue. Let's see. A way to check that would be, if we just do these one at a time, then we're going to get an error because we don't have these events. Okay, I think that this error is coming from solve IVP trying to put different length arrays into the solution because of this, and there's not actually a way for us to fix it. So I'm going to move on and just finish up with the main idea that the blue line is the solution to an ODE. We coupled it with some events, and those events allow us to find minimas, these red dots, zeros, the orange dots, or the maximas as the green dots. So that's extremely helpful in all kinds of ways. You can, any kind of function you can write that uses properties of the solution that are equal to 0, like you could even say print when is the solution equal to 0.5 and get these points. Let's just try that. So let's do event 3. And we're going to return y minus 0.5. And so that's going to be 0 whenever y is equal to 0.5. And then we'll add event 3. So you can have as many of these as you want. And you can, if you set instead of, or in addition, event2.terminal to be true, then it would stop the integration. But I don't really want to do that yet. So let's just do 3 here. Maybe I'll make this a square, and we'll make it a blue square. All right, and so you can see here are where the solutions that are equal to 0.5. So you can do all kinds of interesting things with this. So I hope you found this helpful, and now you know how to find different points in different parts of your solution using events with solve IVP. Thanks. See you next time.